So now that we've defined a linear equation, our next step is to really get a definition of a system of linear equations. So we'll start with a finite set for now of linear equations. In variables x1, x2, all the way up to xn is called a system of linear equations. Or, more concisely, a linear system. A sequence of numbers is a solution of the system if the replacement x1 equals s1, x2 equals s2, all the way to xn equals sn, if this replacement is a solution for every equation in the system. So let's look at an example, and we'll make a system with three variables. So for x1 minus x2 plus 3x3 equals negative 1, 3x1 plus x2 plus 9x3 equals negative 4. And so this is a system of three unknowns and two equations. Now this has a solution. I'm not saying only solution, but I'm saying there is a solution where x1 equals 1, x2 equals 2, and x3 equals negative 1. And we can see this if I do the substitution on the first equation. I get 4 minus 2 minus 3. So 4 minus 2 is 2, minus 3 is negative 1. So that satisfies the first equation. And if I do that replacement on the second equation, 3 times 1 plus 2 plus 9 times minus 1 equals negative 4. So I get 3 plus 2 minus 9, or 5 minus 9, negative 4. And so this sequence, 1, 2, negative 1, is in the replacement satisfies both equations. Now, as we showed with the lines, not all system of equations have a solution. So if we look at the system x plus y equals 4 and 2x plus 2y equals 6, well, if I multiply the top equation by 2 and then I subtract the two equations from each other, I get 0 equals 2. And that means this isn't true, and so there's no solution to this system. We can even kind of see it here without the subtraction, is this is equal to 8, but the same thing is equal to 6. And that's contradictory. And so if a system has no solutions, we say it is inconsistent. If there is at least one solution, we say it is consistent. So, in general, we can say every system of linear equations has no solutions or exactly one solution or infinitely many solutions. As soon as you parameterize a solution and that parameter works consistently, then it will have infinite solutions because that parameter can go to infinity. So what we're going to do here is we're going to take a system of equations in its most general form. So we're going to have the first row, first variable, plus the first row, second variable. So noticing my number convention here, I'm going to talk about the row or the first equation and which variable the number is associated, the constant is associated with. We're going to have to use these double subscripts to describe position. And since this is a singular number, not a series of coefficients, we will count the rows off with these. And so notice this is a row column and B counts rows, because what happens is this will be the second equation, which creates a second row. And we'll go all the way down to B sub n equations. And so here we have n unknowns and n equations in this case. And I could generalize this because I could have less equations than I have unknowns. So let's make this m and n. And so I have m equations and n unknowns. And I identify each equation with the first number. And I identify the unknown that a constant is associated with the second number. And there's a geometry in this. And so what we can do is we can take this whole problem and we'll create what's called an augmented matrix. We're going to ignore the unknowns and the plus signs because we know they're there, and we're going to pay account to the equal sign. And so we can abstract all the information from this in an augmented matrix. So the same system of equations we'll write like this. So we're going to put a bracket around it, and we're going to talk about the coefficients that come before each variable. And then we're going to talk about what's on the right-hand side of the equal sign. Some texts use a line to show that this is an augmented matrix, but we're not. We're going to not have that line in there. And our augmented matrix then will have a row for each equation, a column for each unknown, and a column for the constants that the linear equations are equal to. And because we have made the geometry hold it, we can get back to the original equation by adding the plus signs and the equal signs here, or the original system of equations. So we let the geometry hold all the information for us. And so let's look at an example here. I'm going to have a system of equations in 3 unknowns. Let me make that 2x3. And we can transfer this to an augmented matrix by looking at the coefficients. So that's 1. That's 1. That's 2. And we have the 9. So the first coefficient in the first row, second coefficient in the first row, the third coefficient in the first row, and the constant. The next coefficients with the sign. And this object that we're creating, this matrix, has all of the information that the system has. And so what we're going to do is we're going to have some rules on what we can do with the matrix to solve it. We're going to abstract everything we've done with solving systems of equations in regular algebra into manipulating the matrix. What would be nice is if I had x1 equals an answer for it. So for right now, we'll say that's b1. X2 equals b2. and x3 equals b3, that matrix would have 1 for x1, 0 for x2, 0 for x3, and b1. It would have 0 for the next equation, 1, 0, b2, and 0, 0, 1, b3. Notice how these line up with each equation, and we have this diagonal set of 1s with zeros everywhere else, but that 1 is telling me what x1 is. That one is telling me what x2 is. And this one is telling me what x3 is. And so our goal is to manipulate this so we get this in some form so we can solve. And so we're going to need some rules. So there are 3 operations we're going to allow ourselves to do on these augmented matrices. We're going to be able to, 3 rules of matrix manipulation. One, we can multiply a row by a non-zero constant. And that's the same as multiplying an equation by a non-zero constant. So for example, if I had the equation x plus y equals 3, if I multiply this equation by 5, 5x plus 5y equals 15. And these are the same equation. Right, we can simplify this to the other. In matrix form, that would be 1, 1, 3 for the row it was in. And if I multiply the row by 5, I get 5, 5, 15. So we can multiply a row by a non-zero constant. We can interchange two rows. And that's the same if I had 2 constants, or 2 equations, writing one before the other. The order the equations in does not matter for a system, so the order the rows are in does not matter. And 3, we can add a multiple of one row to another row. And that's the key to like the elimination method in algebra. When you, let's have x minus y equals 6 and 3x plus 3y equals I'll say 19. If I multiply the top row by 3 and add these 2 equations together, the y's will cancel out and I'm left with 6x equals 37 and x is 37/6. And that's something we did algebraically, where we could multiply one equation and add them, and we were looking to eliminate a variable, so we got something in terms of one variable. Well, we can add a multiple of one row to another row. And so these all together are called elementary row operations. So I'm going to write them down here again. These are important. Multiply a row by a non-zero constant. Two, exchange 2 rows. And 3, add a multiple of one row to another row. And what we're going to want to do is, in the next video, we're going to solve some system. We're going to use some elementary row operations, really give ourselves a notation for elementary row operations, and then use them to find some solutions to systems of equations.